Okay, so good day everyone. So for today, we're going to have a week three, no, the segment one, the boot process and the MBR. So as what I mentioned, this is week three, no, segment one, and we're picking up where we left off in our last video presentation when we talk about partitions. In that video, no, we had discussed the operating system specific partitions for which we use tools like this label on NetBSD, format on OmniOS, and FDisk on Linux. So we also hinted at the difference between these partitions and so-called BIOS partitions used by the master boot record or MBR, which gets us to and so-called BIOS partition used by the master boot record on master boot record or what we call MBR, which gets us to today's topic, no, the boot process on a high level as well as a fairly detailed look at the MBR. Okay, so when we boot up a system, we'll like see messages, like this on the console. Here's the display of a NetBSD boot loader. As you can see here, it is a BIOS boot, loader, and it offers you an interactive menu to select different ways of booting. If we let it time out without a selection, then it will simply begin the normal boot process and boot the NetBSD kernel, which generate these green messages shown here, displaying the hardware as it is initialized it. At some point, then it hands control off to the init process, which we can see here when the boot process switches colors in it, then continues the bootstrapping process, mounting the file system, bringing up networking, and launching whatever daemons the system is configured to start before leaving us with the login prompt. So we can break down this process that we just saw into these individual steps. So when we power on the physical server, what is the first thing that happens? Now, well, you may hear a series of beeps, which may indicate to you that there was a hardware failure of some sort. Or you may not if you're lucky. That is, before anything else, the system perform power on self-test, where it checks for basic sanity of the world. That's there's some memory, a system processing unit, what storage devices may be present, and which ones the system is configured to boot from. Once that's complete, the system will look for the so-called first stage boot loader. Traditionally, that mean looking for a specific signature and executable code in the first sector of the disk. It's supposed to boot of the boot sector. So you probably heard the term MBR, or master boot record in this context, which is exactly what we're talking about here. So the first stage bootloader may then hand off control to a second stage loader. And this might be needed because, as we will see in a minute, the first stage bootloader is necessarily very limited in size, so that if you want to perform something more complex than a simple boot, you may find some special code somewhere else to jump to before you can even find and load the kernel in question. Now, after the second stage bootloader, eventually, you load your kernel. Now, in the case of a virtual machine such as on AUS, that be a special kernel, let's say, for example, if you're using Zen for virtualization, you'd be booting the Dumo hypervisor kernel. All of these steps are happening on the physical host, which is a worthwhile distinction, since after that kernel has booted, it would then start the respective guest domain, which goes through the same process and loads its kernel, which then, as we saw in our opening sequence, so initialize the hardware it finds, virtual hardware in this case. So these last three steps are thus happening within the virtual host in kernel space before the kernel hands off control to init or system D, no? Or whatever is used to start the various services. So if the system you're bringing up happens to be a web server, that application would then run, bind the right network port, and finally serve content. So these last few steps are still executing when the virtual host, but now are running in unprivileged mode or user space. So this is simplified, complete boot process from power on to serving traffic. But today, we only care about the first few steps where we look at how we even get to the kernel. So when you power on a physical server, this is what you might see first. This is an example of an American Megatrends BIOS, the basic input-output system showing a successful power on self-test. Normally, this would now simply jump into the boot sector of the configure boot disk, but it may also let you configure certain aspect. That is, even though this piece of software is necessarily simple, it is still allows for some flexibility. And since the BIOS open sits now on a read-only memory chips on the motherboard and thus isn't quite soft. Well, soft, we don't even call it software. It's harder to change, but it's not quiet hardware. So we call it firmware instead. So this screen shows an example of a BIOS configuration menu allowing us to select the boot order of devices, for example. But the BIOS dates back to the CP/M operating system from the 70s and was originally proprietary to IBM PCs, then reverse engineered by others, but not standardized and open specialized for a specific motherboard or other hardware. So the BIOS also had a few technical limitations, which we saw in our previous videos when we talk about the problems certain BIOSes had in addressing large disks. So, so we now have the unified extensible firmware interface, which provides a modern and standardized way of interfacing between the operating system and the underlying firmware. But as so often, it's important and useful to understand the history and how things were done in the olden days, which in turns out is still very frequently how things are done today, such as for backwards compatibility reasons, which is why we're now going to look not to UEFI, but instead at the traditional master boot record, which the traditional BIOS expect to find in the first sector. That is, in the first 512 bytes of the boot disk. So that's right. No? The master boot record is only 512 or 512 bytes in size. So within this 512 bytes, we have to fit a pair bit of information as well as the code needed to boot the system. So let's see what that looks like. So at the end of the first sector, we expect to find the magic bits 0 times 55 and 0 XAA. No? So the presence of these two bytes indicates to the BIOS that this is a valid boot sector. Then the first or the 64 bytes right before hold the partition table. Now this partition table is different from the partition table we discussed in our last video. No, this is the BIOS partition table which describe which OS partitions the BIOS can see. Then a BIOS partition table entry then is 16 bytes. So as what we have here, So 16 bytes in size, no? So we can have exactly 4 of this partition. So we have 1, 2, 3, 4 partition. No? But we know that our operating system may want to carve up the disk into more than just 4 partition if it needs to. And that alone illustrates the need for a distinction between the BIOS and the OS partition. That is, the BIOS partition really only defines which parts of the disk are allocated for a given operating system. What the operating system then does with that slice of the disk is entirely up to it. We need to remember that in our previous discussion, we showed that the BSD system used the D partition in their OS disk level to reference the entire physical disk, and the C partition to reference the part of the disk dedicated to this entire physical OS. No? This C partition is effectively what we're defining here, and the OS can then create additional partition therein. Anyway, so with 2 bytes, for the magic number of 64 bytes for the partition table, we're left with 446 bytes, no? For a stage 1 bootloader. That is, everything needed to bootstrap the system needs to fit into this 446 bytes here, which is why we are open talking about this being the stage 1 bootloader. It's just enough code to bring up the system to a point where it can perhaps reach into other sector on the first track to then find more complex code to transfer control to. That code is then known as the stage 2. Bootloader GNU Groove is an example of a bootloader that may contain multiple stages. But back to partitions, no? So we have a partition table consisting of 64 measly bytes, leaving us with an even near 16 bytes to describe the disk. How do we organize these 16 bytes? So the first byte tell us whether this partition is active or not. Then we get 3 bytes no to address the per sector of the disk using the cylinder head sector addressing schema we discussed in our video later. Then, sorry. As what we have here, no, these 3 bytes, no. Wait. Yeah, this one. These 3 bytes are defined like so. So the first byte identifies the head. Then at 8 bits, that means we can address at most 256 heads, which was a limitations we have previously mentioned. Now, the second byte is a bit less straightforward. Rather than giving us a whole byte for the sector, we only get 6 bits now with the first 2 bits of this byte being reserved for the high bits of the cylinder address. So the largest sector number we can address is the 64. And in the third byte, we get 8 bits. So as what we have here, no? 8 bits. No, for the cylinder address. No? Plus the 2 bits stash, no, in byte 2 above, we get 10 bits for the cylinder. No? Then meaning, no, we get 10 bits for the cylinder, meaning a maximum of 1024. No? After this, we get 1 byte to identify the partition type for the operating system in question, no, NetBSD or Linux, let's say for example. Then we get another 3 bytes, no, for the CHS address. No, ito po yun. For the last sector, which we also chop up just like before. But now, let's recall that with the limitations we have here, we couldn't address this above a certain. By today's standards, pretty small limit, no? So we had changed our addressing schema to use logical block addressing. So here, we get 4 bytes for the LBA of the per sector and 4 bytes for the last sector. So now we have two ways of addressing sectors. How do we get from one to another? When we can start with the LBA of the address, and then it determines the C, H, and S values from that using this formula. And then use those values here. Okay, so now that we know what these bikes look like, no, we should be able to create a boot sector with a valid partitions today and partition table entry for any disk simply by writing the required bytes to the correct offset. Okay, all right, now let's give it a try, of course. And we start out again as usual with the new NetBSD, no, instance, and the create a volume to play around with. Let's make it 3 gig in size this time, no, and we wait for the instance to come up and attach the volume using another shell functions to have ourselves some typing. Okay, so log in on the instance and inspect the disk via DMEG or DMES. No? There are actually there's our root disk and our newly attached disk, no, yung XBD1. And let's look at the BIOS partition table of the root disk via the fdisk command. No, we see the logical geometry of the drive as well as the BIOS geometry. So the partition table shows the first partition to be of the type NetSBD and active starting of sector 2048. No, uh, and with the shown cylinder head sector addresses. So if this shows us all this information, but what does it actually look like? Let us the DD command to retrieve the first 512 bytes of the disk and display them as hex via the hex dump utility. So here we go. So all of these bytes here are the actual boot code with the first partition being defined in this 16 bytes over here. And all of the way at the end here, we see the MBR signature, the 0x55, 0xAA. No? And so let's take a look at the first partition alone. We know it's 16 bytes in size at offset 446. So here it is. No? And so this 16 bytes describe the first partition entry shown by fdisk like this. Now, okay, so far so good. No, now what does our second disk look like? No, the F disk shows that there are no partitions defined, no active partition. So if we look like at the bytes on that drive, then no surprise, they are all null. No, okay, so how do we turn this no into this? Now let's start at the beginning. Well, the end, I suppose, na note how F this tell us the partition table here is invalid because there's no magic number at the end of the sector. Okay, so the beginning of this partition is sector 2048 no, or 2048 because the entire first track is open. uh reserved no for additional bootstrap code as we mentioned earlier. No, so now we can use our formula to calculate the CHS address from the LBA address, with our LBA address in this case being 2048. No, so divided wait. Okay, okay, so 2048, so divided by the 16065 is obviously 0, which will be our cylinder value. So we then have a remainder of 2048. So let's divide that by the number of sectors bit per track, which gets that 32. And 32 decimal is 20 hexadecimal. So our header value is 20 hexadecimal. And finally, the sector value is the remainder plus 1. Now, so we can now write these 3 bytes, no? Head sector, cylinders to offset 447 for the starting sector. And let's check. There's we go starting sector at cylinder 0, head 32, sector 33. So now we need the last sector. So we know we have a total of these many sectors, but the per sector contains the MBR here. So let's subtract that and divide it by the number of sectors per cylinder to give us the cylinder address number in the decimal 391 in this case. No, this remainder is 10040. So as what we have here, no, giving us the decimal of 159 actually, no. Then so our headers byte in hexa is then 9F. And now the value of our sector is 24 decimal. But remember, we no need to puzzle together the bits for the cylinder and sector. So we need to convert this to binary. So which give us 11000, no, for the header bits. For the cylinder now, we need 391 in binary, which looks like this. No? So now we combine the binary bits back to hexadecimal. For this, we now grab the first two high order bits of the cylinder number 0 and 1 in this case, followed by the 6 bits now representing the sector, giving us 58 hexadecimal value. No? And 8 bits of the cylinder number converted to hexadecimal value. So now we have CHS bytes 9F, 58, and 87. Let's write those to offset 451, and let's of course discuss this one. No? So all right, no. Let's recap. Remember, we started out discussing the typical boot sequence. We said that it all starts with some basic firmware, which may be the BIOS or UEFI and others, which may perform a post check and initialize the hardware it sees before it transfer execution to the first stage bootloader, such as the MBR, which then may continue the bootstrapping process by handling control to the second stage bootloader, which then loads the kernel, which then ultimately handling control to the second stage bootloader, which then loads the kernel, which then ultimately hands control off to us user land process like init. No? Now, one thing to note here is that in virtualized hardware, some of these steps repeat, some may be skipped, and some may be simulated as our virtual host initializes as virtual hardware as it boots up. But ultimately, we arrive at a running system as we're looking at the boot process here and having understood the MBR some detail. Okay? Actually, this would be your exercises, no? But I'll give you other exercises rather than this one. And this will be the link, of course. But prior to that, I'll just want to show you, no, the steps, no, the actual demonstrations of what I have discussing earlier, no. So if you have an additional input or queries, do not hesitate to push your question in our chat box, so we could able to address all your question as early as possible.
Hello, and welcome back to CS615 System Administration. This is week 3, segment 1, and we're picking up where we left off in the last video when we talked about partitions. In that video, we had discussed the operating system specific partitions, for which we use tools like DiskLabel in NetBSD, Format on OmniOS, and fdisk on Linux. We also hinted at the difference between these partitions and so-called BIOS partitions used by the master boot record or MBR, which gets us to today's topic, the boot process on a higher level, as well as a fairly detailed look at the MBR. So, when we boot up a system, we'll likely see messages like these on the console. Here's a display of a NetBSD bootloader. As you can see, it is a BIOS bootloader, and it offers you an interactive menu to select different ways of booting. If we let it time out, without a selection, then it will simply begin the normal boot process and boot the NetBSD kernel, which generates these green messages shown here, displaying the hardware as it initializes it. At some point then, it hands control off to the init process, which we can see when the boot process switches colors. Init then continues the bootstrapping process, mounting the file system, bringing up networking, and launching whatever daemons the system is configured to start, before leaving us with a login prompt. So we can break down this process that we just saw into these individual steps. When we power on the physical server, what is the first thing that happens? Well, you may hear a series of beeps, which may indicate to you that there was a hardware failure of some sort, or you may not, if you're lucky. That is, before anything else, the system performs a power-on self-test, where it checks for basic sanity of the world, that there's some memory, a CPU, what storage devices may be present, and which ones the system is configured to boot from. Once that's complete, the system will look for the so-called first-stage bootloader. Traditionally, that would mean looking for a specific signature and executable code in the first sector of the disk it's supposed to boot off, the boot sector. You've probably heard the term MBR, or Master Boot Record, in this context, which is exactly what we're talking about here. This first-stage bootloader may then hand off control to a second-stage loader. This might be needed because, as we will see in a minute, the first-stage bootloader is necessarily very limited in size, so that if you want to perform something more complex than a simple boot, you may find some special code somewhere else to jump to, before you can even find and load the kernel in question. Now, after the second-stage bootloader, eventually you load your kernel. Now, in the case of a virtual machine such as an AWS, that would be a special kernel. For example, if you're using Xen for virtualization, you'd be booting the DOM0 hypervisor kernel. All of these steps here are happening on the physical host, which is a worthwhile distinction, since after that kernel has booted, it would then start the respective guest domain, which goes through the same process, and loads its kernel, which then, as we saw in our opening sequence, initializes the hardware it finds, virtual hardware in this case. So these last three steps here are thus happening within the virtual host and kernel space, before the kernel hands off control to init, or systemd, or whatever is used to start the various services. If the system you're bringing up happens to be a web server, that application would then run, bind the right network port, and finally serve content. These last few steps are still executing within the virtual host, but now are running in unprivileged mode, or user space. So this is the simplified, complete boot process from power on to serving traffic. But today, we only care about the first few steps, where we look at how we even get to the kernel. So when you power on a physical server, this is what you might see first. This is an example of an American Megatrends BIOS, the basic input-output system, showing a successful power-on self-test. Normally, this would now simply jump into the boot sector of the configured boot disk, but it may also let you configure certain aspects. That is, even though this piece of software is necessarily simple, it still allows for some flexibility. Since the BIOS often sits on a read-only memory chip on the motherboard, and thus isn't quite so, well, soft, we don't call it software. It's harder to change, but it's not quite hardware, so we call it firmware instead. So this screen shows an example of a BIOS configuration menu, allowing us to select the boot order of devices, for example. But the BIOS dates back to the CP/M operating system from the 70s and was originally proprietary to IBM PCs, then reverse-engineered by others, but not standardized and often specialized for a specific motherboard or other hardware. The BIOS also had a few technical limitations, which we saw in our previous video, when we talked about the problems certain BIOSes had in addressing large disks. So we now have the Unified Extensible Firmware Interface, which provides a modern and standardized way of interfacing between the operating system and the underlying firmware. But as so often, it's important and useful to understand the history and how things were done in the olden days, which, it turns out, is still very frequently how things are done today, such as for backwards compatibility reasons. Which is why we're now going to look not at UEFI, but instead at the traditional master boot record, which a traditional BIOS expects to find in the first sector, that is, in the first 512 bytes of the boot disk. That's right, the master boot record is only 512 bytes in size. Within these 512 bytes, we have to fit a fair bit of information as well as the code needed to boot the system. So let's see what this looks like. At the end of the first sector, we expect to find the magic bits 0x55 and 0xAA. The presence of these 2 bytes indicates to the BIOS that this is a valid boot sector. The 64 bytes right before hold the partition table. Now this partition table is different from the partition table we discussed in our last video. This is the BIOS partition table, which describes which OS partitions the BIOS can see. A BIOS partition table entry, then, is 16 bytes in size, so we can have exactly 4 of these partitions. That is, a disk with an MBR can have at most 4 BIOS partitions. But we know that our operating system may want to carve up the disk into more than just 4 partitions if it needs to, and that alone illustrates the need for the distinction between the BIOS and the OS partitions. That is, the BIOS partition really only defines which parts of the disk are allocated for a given operating system. What the operating system then does with that slice of the disk is entirely up to it. Remember that in our previous video we showed that the BSD system uses the D partition in their OS disk label to reference the entire physical disk, and the C partition to reference the part of the disk dedicated to this OS? This C partition is effectively what we're defining here, and the OS can then create additional partitions therein. Anyway, so with 2 bytes for the magic number and 64 bytes for the partition table, we're left with 446 bytes. That is, everything needed to bootstrap the system needs to fit into these 446 bytes here. Which is why we are often talking about this being the stage 1 bootloader. It's just enough code to bring up the system to a point where it can perhaps reach into other sectors on the first track to then find more complex code to transfer control to. That code is then known as the stage 2 bootloader. GNU Grub is an example of a bootloader that may contain multiple stages. But back to partitions. So, we have a partition table consisting of 64 measly bytes, leaving us with an even punier 16 bytes to describe the disk. How do we organize these 16 bytes? The first byte tells us whether this partition is active or not. Then we get 3 bytes to address the first sector of the disk using the cylinder head sector addressing schema we discussed in the previous video. These 3 bytes are defined like so. The first byte identifies the head. At 8 bits, that means we can address at most 256 heads, which was a limitation we had previously mentioned. Now the second byte is a bit less straightforward. Rather than giving us a whole byte for the sector, we only get 6 bits, with the first 2 bits of this byte being reserved for the high bits of the cylinder address. So the largest sector number we can address is thus 64. And then in the third byte, we get 8 bits for the cylinder address, plus the 2 bits stashed in byte 2 above, we get 10 bits for the cylinder, meaning a max of 1024. After this, we get 1 byte to identify the partition type, for the operating system in question, NetBSD or Linux for example. Then we get another 3 bytes for the CHS address of the last sector, which we also chop up just like before. But now let's recall that with the limitations we have here, we couldn't address disks above a certain, by today's standard pretty small, limit. So we had changed our addressing schema to use logical block addressing. So here we get 4 bytes for the LBA of the first sector, and 4 bytes for the last sector. So now we have 2 ways of addressing sectors. How do we get from one to the other? We can start with the LBA of the address, and then determine the C, H, and S values from that using this formula, and then use those values here. Okay, so now that we know what these 16 bytes look like, we should be able to create a boot sector with a valid partition table entry for any disk simply by writing the required bytes to the correct offsets, right? Let's give it a try. We start out again, as usual, with a new NetBSD instance, and then create a new volume to play around with. Let's make it 3 gig in size this time. We wait for the instance to come up, and attach the volume using another shell function to save ourselves some typing. Okay. Let's log in on the instance and inspect the disks via dmessage. There's our root disk and our newly attached disk xbd1. Let's look at the BIOS partition table of the root disk via the fdisk command. We see the logical geometry of the drive as well as the BIOS geometry. The partition table shows the first partition to be of type NetBSD and active, and starts at sector 2048 and with the shown cylinder head sector addresses. So fdisk shows us all this information, but what does it actually look like? Let's use the dd command to retrieve the first 512 bytes of the disk and display them as hex via the hexdump utility. Here we go. So all these bytes there are the actual boot code, with the first partition being defined in these 16 bytes over here. And all the way at the end here, we see the MBR signature, 55AA. So let's take a look at the first partition alone. We know it's 16 bytes in size at offset 446. So here it is. And so these 16 bytes describe the first partition entry, shown by fdisk, like this. Okay, so far, so good. Now, what does our second disk look like? fdisk shows that there are no partitions defined, no active partition. If we look at the bytes on the drive, then, no surprise, they're all zeros. Okay, so how do we turn this into this? Let's start at the beginning. Well, the end, I suppose. Note how fdisk tells us that the partition table here is invalid, because there's no magic number at the end of the sector. Let's fix that. We use printf to write the hex bits 55AA to offset 510 of def xbd1. Okay, so now we note that fdisk no longer complains about the partition table being invalid, but it still says that there's no active partition. So let's create a NetBSD partition here. For that, we need to get the partition type identifier for NetBSD, which is 169. What is 169 in hex? Let's use the BC tool for that. Okay, A9 is the hex value we want. Let's write that to offset 450. And then let's mark this partition as active by writing 0x80 to offset 446. Okay, let's see what fdisk says now. There. Partition 0 is now a NetBSD partition and is marked active. But we're still missing the size and definition of this partition. As we see here, the cylinder head sector definitions are 0. So let's define those. The beginning of this partition is sector 2048, because the entire first track is often reserved for additional bootstrap code as we mentioned. So we can use our formula to calculate the CHS address from the LBA address, with our LBA address in this case being 2048. So 2048 divided by 16065 is obviously 0, which will be our cylinder value. We then have a remainder of 2048, so let's divide that by the number of sectors per track, which gets us 32. 32 decimal is 20 hex. So our header value is 20 hex. Finally, the sector value is the remainder plus 1. So we can now write these 3 bytes, heads, sector, and cylinders, to offset 447 for the starting sector. Let's check. There we go. Starting sector, it's cylinder 0, head 32, sector 33. So now we need the last sector. We know we have a total of this many sectors, but the first sector contains the MBR here. So let's subtract that and divide it by the number of sectors per cylinder to give us the cylinder address number in decimal, 391 in this case. The remainder is 10040, which we now divide by the number of sectors per track per the BIOS, 63, giving us decimal 159. So our headers byte in hex is then 9F. Now the value for our sectors is 24 decimal. But remember, we now need to puzzle together the bits for the cylinder and sector, so we need to convert this to binary. Which gives us 11000 for the header bits. For the cylinder now we need 391 in binary. Which looks like this. So now we can combine the binary bits back to hex. For this, we now grab the first 2 high-order bits of the cylinder number, 0 and 1 in this case, followed by the 6 bits representing the sector, giving us 58 hexadecimal. And the last 8 bits of the cylinder number converted to hex is 87. So now we have our CHS bytes 9F, 58, and 87. Let's write those to offset 451. Okay. What does fdisk tell us? Looks good so far. We have a starting CHS address and an ending CHS. But our MBR also requires the LBA addresses, so let's go ahead and add those. We know the LBA of the starting address is 2048, which is 800 in hex. But the LBA field needs 4 bytes, and it uses little endian byte ordering. So we turn 0800 into 0800. And write those bytes to offset 454. The last sector then is the total number of sectors minus 2048. In hex and convert it to least significant bit first. And written to offset 458. And now fdisk shows us a proper partition with the right size and the right addresses. But of course, there's an easier way to do this. Let's wipe out the MBR by overriding it with zeros. There. All zeros. Then we can use fdisk to specify that we want to activate partition 0 with a specification of 169 for NetBSD, beginning at sector 2048, and of the given size which then looks just like we had manually written to the disk. This shows that there really is no magic to any of the tools we use to manipulate our disks. It's all just a question of knowing which bits to write to which place. That, and that it's rather useful to be able to use DD, hexdump, and BC to manipulate and write individual bits and bytes. Alright, let's recap. Remember, we started out discussing the typical boot sequence? We said that it all starts with some basic firmware, which may be the BIOS or UEFI, etc., which may perform a post check and initialize the hardware it sees before it, transfers execution to the first stage bootloader, such as the MBR, which then may continue the bootstrapping process by handing control to the second stage bootloader, which then loads the kernel, which then ultimately hands control off to a userland process like init. Now, one thing to note here is that in virtualized hardware, some of these steps repeat, some may be skipped, and some may be simulated, as our virtual host initializes virtual hardware as it boots up. But ultimately, we arrive at a running system. And we're looking at the boot process here, and having understood the MBR in some detail, let's consider some additional exercises for you. AWS instances allow you to get the output sent to the virtual serial console, and different operating systems display different levels of detail, and of course the boot process is different for each OS. So a good exercise for you would be to compare the output of different operating systems. Spin up a few instances, say a NetBSD, FreeBSD, Ubuntu, Fedora, or OmniOS instance, and compare the output of the console. In particular, pay attention to the file system or disk-specific messages. Make sure you understand what the output means. I've put sample output into individual files at this URL, but I still also recommend that you run the AWS commands to get more familiar with that part. Next, I want you to think about the security of the boot process. As we've seen, there are several layers to this process, and different pieces of software. The firmware from the ROM on the motherboard, the bits written to the boot sector that we normally don't think about. How can we remain assured that nobody has tampered with the software or firmware? The concept of trusted computing comes into play here. Look up the terms remote attestation, for example, or secure boot in this context. Finally, you may have noticed that we still haven't gotten to the point where we're actually using the file system, or what that might actually look like. Let's fix that in our next video, shall we? Alright, that's it for today. See you next time, and thanks for watching. Cheers.
Okay, so this time, this week 3 segment 2. So in our last video, we spent a fair amount of the time looking at the boot sector and the master boot record, no? In which we define the BIOS partition. And this discussion, we had discussed the file system or OS partition on which a file system would then be created. But before we go ahead and do that, let's first think a bit about what it means to be file system and what is the fundamental goal of file system and what is the is it for so, as we all know, the primary functions of a file system is to store cut figures, right? No? So how do we do that? Well, we can simply try to slash all the cut photos in the disk one next the other. So that doesn't sound too complicated. So let's give it a try. So file system describe our data. No, with file system we had folders, access control, and name files. Without them, our disk would be just a soup of bits. No, we wouldn't know where everything was stored. No, where things start or end, or any external information, the metadata. So a file system numbers one job is to keep our data safe. So we want our data quick to access, easy to manage, and above all, it must be correct and in the place where we put it. No? Storage hardware failure, hard drive crashes, no, are all too common statistically. This means that we need to look deeper into storage management if our data is valuable to us. It's easy to ignore file system and go with defaults. No, in today's Linux, no, that means the X4 or XFS file system, but we have other more advanced option, the BRTFS and ZFS. And this next generation file system let us work more flexibility and safely with larger amount of storage. So over time, these two file system, now we have the ext4 and XFS. So these two file system had grown to serve very similar needs. Now they're fast and reliable journal, no, file system. No, Ubuntu was used ext4 by default since 200 grams Karmic Koala release, no, 2010. Red Hat's Enterprise Linux 6.0 also used ext4. Real 7.0 moved to XFS in 2004. So a file system is much a fundamental piece of a stable system that kernel and distribution maintains, moves slowly and carefully in adapting charges. So if we install Ubuntu or Debian, now today our storage will use ext4. If we install Red Hat, Enterprise Linux or SUSE, we'll get XFX. No? So yesterday, no, high-tech journals extend and limited checksums. No, we have, of course, a file system, no, in journals. No, a file system journal writes a duplicate log of all changes to the file system. If a write to the file system is interrupted, no, the system examines the journal and play it back to minimize data loss and file corruption. Extent, no, the traditional file system would maintain a map of their context or contents, no, block by block. So a default block is usually 4.096 bytes, no. So as storage has increased, we can imagine how large these maps have become instead, no. XFS and ext4 map out piece of data in large chunks called extents, no. Specifically, an extent map is two numbers, the starting block address and the length of the extent, no, in blocks. No, this works well for large volume and large files, removing the need to track the file membership of each block. So checksums, no, how do we know our data has not come corrupted? Now, one way is by calculating a checksum. So a shorter magic number that changes when our larger data changes. So we used to do this by running a check and repair program. The difficult to pronounce FSCK, XFS and ext4 now calculate a checksum on metadata and their journal files. And this is useful actually through far less complete than the block by block checksum of BTRFS and ZFS. Although both ext4 and XFS are excellent at what they do, neither are suited to some of today's more complex storage challenges. Now, the extended file system or the X file system, it remains the most popular file system in use with Linux, starting with ext in 1992, and the file system quickly moved to ext2 in 1993, grew to add a journal with ext3 in 2001, and got a future profiling tune up in 2008 with ext4. So the ext4 file system continues the philosophy of its predecessor: be fast and fix if it breaks. No? However, ext3 and 4 add data safely features like a journal and limited checksums. So ext4 also makes possible larger volumes in files. Its adoption, no, of extent further helps with larger files like media and some databases. No? But ext4 also works well with collection of many smaller files. No? It removes ext3 previous cap on a subdirectories. No? Subdirectories. There is a reason that ext series of file has lasted so long as the default for Linux. No? It's the well-tested workhorse that prioritizes speed. and good enough data validation. We have also XFS, no? XFS. Okay, 90s for big iron actually, no? So Silicon Graphics Incorporated created XFS in 1993 for their IRX Unix OS, no? SGI famously pushed the limit of computer graphics production. They relied on their own custom high-end and highly parallel hardware to achieve it, no? And as a result, SGI required actually, no, a file system that could reliably address huge files using multiple CPUs and drive controllers. Reliability meant keeping a journal to avoid the corruption. No? Addressing large files meant making XFS 64-bit, no? And allowing multiple CPUs to read and write these giant files meant the developer of XFS needed to remove the standard practice of placing lock around an inode during access. So we can manage, no, we can imagine, no, the additional complexity of allowing simultaneously access by potentially hundreds of CPU cores, no. But designing a software system in fine-grained paid off for their highly parallel hardware, like Mac OS and iOS fits Apple hardware. XFS fit SGI's ecosystem. So XFS was ported to Linux and entered the kernel in 2001. It's now available and reliable on just about every Linux distribution. If we're building a system with large storage requirement, large files, and multi-threaded input-output, we shouldn't consider XFS. But for similar and lighter loads, ext4 may suit us better. Will our system be grinding through media file or big data? So if we we should look into XFS or one of the next generation file system. We will be running a microservice. No, if that's the case, we may want to stick to ext4. We have also what we call actually, no, before with this one, no, RAID and logical volume managers. No, although detailed examination of RAID and logical volume option is a matter for a separate article, we need to understand how they interact with file system, because a RAID and logical volume managers do different things, but both allow us to think of multiple physical disks as one abstract volume. Instead of creating our file system directly on the block device, we add the disk to a collection, then think of the collection as one device with one file system. Both the SDA5 partition and the SDB drive are physical drives, no, collected into a single volume group and allocated into logical volumes where the file system live. No, notice how the root mount point, no. Modern Linux has been doing this for years with LVM, no, allowing us to use all of the space available or to set some aside or as leave mirrored copy. We can also add new physical disks and resize our volumes and file system. It's it's handy to be flexible, and how we choose to spread out our data carries both risk and rewards. If one disk dies, no, if one disk dies, we lose data. How about if we use 10 disk and 2 die, no? So the next generation file system, of course, later on I will just want to discuss this one later, right after our video presentation, no? Because I just want to show you on how we'll be able to apply the file system and how we'll be able to manipulate the file system in Linux, no? Actually, this will be the references of our video presentation. So if you have some question again and verifications or additional input, do not hesitate to post your question in our chat.
Hello, and welcome back to CS615 System Administration. This is week 3, segment 2. In our last video, we spent a fair amount of time looking at the boot sector and the master boot record, in which we defined the BIOS partition. In the video before, we had discussed the file system or OS partition, on which a file system would then be created. But before we go ahead and do that, let's first think a bit about what it means to be a file system. What is the fundamental goal of a file system? What is its purpose? As we all know, the primary function of a file system is to store cat pictures, right? So how do we do that? Well, we can simply try to stash all the cat photos on the disk, one next to the other. That doesn't sound too complicated, so let's give it a try. Here we again start out with our default NetBSD instance with an attached volume as before. We'll now pretend to be a file system for the disk XBD1, and we have 1 gig of space to manage. So let's write our first cat picture to the disk. We use printf and dd to write the bytes right to the beginning of the disk. If we now look at the data on the disk, we see that our cat picture consists of 4 bytes. F0, 9F, 98, B8. We have successfully stored our first file. To read this file from disk, we simply read the first 4 bytes. There we go, there's our cat. Okay, now it's time to store our second cat photo. Since we don't want to waste space, we'll write it right after the first photo. And we can see here our 8 bytes of data. If we read all of those bytes, we get back both of our files. But we can of course also fetch them from the disk one by one. Okay, so far so good. Now let's create our third cat photo. 2 cats in snow. We'll write this data right after the second picture. If we read all the data in a single 512-byte read, we get all 3 photos. And of course we can grab the second photo individually, but if we try to grab the third photo, we realize we need to know how large it is. Just assuming 4 bytes per photo will not work, so we kinda need to count. Here's our first pick, there's our second pick. So nope. There, 14 bytes. So this illustrates a problem with our very naive approach. In order to be able to retrieve files individually, we need to know where they start and where they end. That is, we probably want to assign specific areas for each file. Let's set aside one area on the disk for each cat photo. And let's make sure that we only put one cat into each bucket. Then we'll always know exactly where each cat pic starts. So let's illustrate that approach. Let's zero out our disk and start from scratch. Again, we can write our first cat photo directly to the beginning of the disk. Now, our second cat photo, however, will write to offset 512. That is, we declare that each of our buckets will be 512 bytes in size, so we always know exactly where the next photo will start, at offsets incrementing in 512 bytes. Now we can easily retrieve the file by simply reading a full 512 bytes and by adjusting the offset. So, in hex, this is what the data looks like on a disk now. First bytes right here, second bytes at offset 512, and the bytes for the third file over here. But note that of course we're wasting a fair bit of space. Our photos are less than 512 bytes in size, but we have all this empty space here between the 512 byte offsets. In addition to read the files, we actually did read a full 512 bytes, even though we only needed 4 bytes for the first 2 files and 14 bytes for the third file. So maybe we should add some metadata to each of the files. So let's start over once more. This time, we're prefixing the file data with the file number and the size of the file in bytes. That way we can later easily determine exactly how many bytes we will need to read. Here's our second file, also 4 bytes in size. And here's our third file, 14 bytes in size. So now on disk our files look like so. The file data for each file is prefixed with a 1 byte field indicating the file number and a 1 byte field for the size, followed by the actual contents of the file. And so we begin to associate metadata with our files, the file number and size in this case. But of course we will probably want to add additional file attributes, additional information about our cat photos. So we can define a new format, where we specify that we use 16 bytes of metadata, a 2-byte identifier, 4 bytes for permissions such as user, group, other, read, write, execute, as we're used to from our Unix file system, a single byte representing the numeric owner of the file, 1 byte for the group, and then we reserve 4 bytes for the size. 4 bytes seems a bit better than just 1 byte, since with just 1 byte the maximum file size we could represent would be 256 bytes. And then we decide that it might be even better to separate the metadata from the file data altogether, since the 16 bytes here will be consistent for every file, but the file data will be variable in size. So we decide to place the metadata at the beginning of the disk, and the actual file data will write somewhere else on the disk. Now in order to be able to map that data to the file in question, we then include the offset here as part of the metadata. Now this starts to look a bit more like a file system, doesn't it? Let's see what our simple file system would look like in our simulation. So let's begin. We write 2 bytes file number, 01 in this case, followed by 4 bytes of permissions, 0744 here, followed by the user ID and group ID, both 0 in this case, followed by 4 bytes file size, which in this case is just 4, followed by the offset of where we find the actual data. So this is just the metadata for the first file now, and with that committed to disk, we can now write the actual file data to the offset we had specified in the metadata. There. Our second file now gets its metadata, file ID 2, and let's say file owner and group ID 1, and because we know the offset of the previous file, we can now write the file data directly after that, so to offset 1004 hex. And appending the metadata directly after the metadata of the first file. And here come the file contents to offset for 100. So if we now look at the first 32 bytes on the disk, we should find the metadata for the two files. File 1 over here, and file 2 over here. Having determined the offset of the file from the metadata, we can then retrieve the file contents. And there you have it. A really simple file system with a separation of metadata from file data. And this is to some degree, and at least conceptually, how file systems work. But before we take a break, here's just one more thing I want to show you, and that's an illustration that a storage archive format really is rather similar to a file system. Here, consider this directory, /temp. Let's create a few normal files. When we run ls, we can see all the metadata of the files, the inode numbers as well as their permissions and ownerships, etc. And of course, we can display the file contents of our cats using, well, cat. Excellent. So now we can use the tar utility to create an archive of these files with all their metadata. But instead of writing the archive to a file as we might usually do, we'll simply write it directly to the raw disk. And this is what that looks like when we inspect the bytes in hex. Here we see the structure of the archive, and I think that you will find that this looks somewhat similar to the format we had created for our trivial file system. That is, at certain offsets we find metadata associated with a file, including ownership and file names, before we then, over here, find the actual file data, our hex bytes, F0, 9F, 98B8. And here's the second file, and the third file. And just like we could write the data to the raw disk, so can we read the data from the disk and pipe it directly into the tar utility, which can then extract the files with all its metadata. So this illustrates that you don't need a file system on the disk device, so long as you write the data in a format that you understand and have defined. Or rather, that there is no meaningful distinction between an archive file and a file system snapshot. But okay, let's recap before we take a break here. In our next video, we will no longer have to pretend to be a file system after we just covered here. But we did learn that, well, the file system is responsible for storing the data on the disk, obviously, and that in order to read or write files, we need to know where on the disk we're writing the actual data. But we also know that we need some metadata, and this metadata may actually be stored separately from the regular file data. And with that, the bottom line is that on a high level, a file system really just describes a data storage format. Now, of course, there are other considerations, especially with respect to efficiency, but roughly speaking, we now know how the file system works. In our next video, we will look at the traditional Unix file system, or UFS, and that file system implements some of the things we discussed here in this video. Before we go on to that segment though, do play around with your virtual disks and your cat photos, as well as to replay the tar as a file system format example, to make sure you understood these concepts, okay? Great. Until the next time, and thanks for watching. Cheers!
Okay, again, Linux file system is a structured collection of files on a disk drive or a partition. So a partition is a segment of memory and contains some specific data. So in our machine, there can be various partition of the memory. Generally, every partition contains a file system. Now, in the general purpose computer system needs to store data systematically so that we can easily access the files in less time. No? It stores the data on hard disk, no, or some equivalent storage type. No? There are maybe below reasons of maintaining the file system. Number one, primarily the computer save data to the RAM storage. It may lose the data if it gets turned off. However, there is non-volatile RAM, no, the flash RAM and SSD, no, that is available to maintain the data after the power interruption. And of course, data data storage is preferred on hard drives as compared to standard RAM. As RAM costs more than disk space, so the hard disk costs are dropping gradually comparatively the RAM. So the Linux file system contain the following section. No? We have the root directory, yung backslash, no? Specific data storage from ext3, ext4, btrfs, xfs, and so on. No? A partition or logical volume having a particular file system. So Linux file system is generally a built-in layer of a Linux operating system used to handle the data management of the storage. It helps to arrange the file on the disk storage. It manages the file name, file size, creation date, and much more information about the file. No? So Linux file system has a hierarchical file structure as it contains a root directory and its subdirectories. All other directories can be accessed from the root directory. So a partition usually has only one file system, but it may have more than one file system. So a file system is designed in a way so that it can manage and provide space for non-volatile storage data. So all file systems require a namespace that it is a naming and organizational methodology. The namespace defines the naming process length of the file name or a subset of characters that can be used for the file name. It also defines the logical structure of files or a memory segment, such as the use of directories for organizing the specific files. Now, once a namespace is described, a metadata description must be defined for that particular file. So the data structure needs to support a hierarchical directory structure, and this structure is used to describe the available and used disk space for a particular block. It also has the open other details about the file, such as file size, data in time of creation, update, and last modified. Also, it stores advanced information about the section of the disk, such as partition and volumes. No? The advanced data and the structure that it is represent contain the information about the file system is stored on the drive, and it is distinct and independent of the file system metadata. So Linux file system contains two-part file system, software implementation architecture. No, so again, we have kernel, virtual file system. So either ext3, HPFS, BF80 or BFAT, ext4, and FreeBSD. Then the hardware, no? So the file system requires an API, no? Ano nga ulit yung API? Kindly type, no, in our chat box what is API, no? So this will be a what? Okay, so please encode, no? What API is, no? Oh, again, API is the application programming interface to access that functions calls to interact with file system components like files and directories API. So thank you sa lahat na nag-reply. What is API? Because API facilitate tasks such as creating, no, deleting, and copying the files. It facilitates an algorithm that defines the arrangement of files on a file system. Sige nga, ano nga ulit ang ginagawa ng API? Paki-type nga sa ating chat box. So, the first two parts of the given file system together called Linux Virtual File System. It provides a single set of commands for the kernel and developers to access the file system. This virtual file system requires the specific system driver not to give an interface to the file system. In Linux, no, the file system creates a tree, no, structure. All of the files are arranged as tree and its branches. So the topmost directory called the root, no, yung backslash directory natin, all other directories in Linux can be accessed from the root directory. Ano nga ulit yung mga features ng Linux in file system? So, paki-type nga sa ating chat box. Okay, number 1, we had, yes, sige, please. Paki-type po, sino po ang may alam ng some features ng Linux file system, no? So number 1 is specifying paths, no? Linux does not use the backslash, no, to separate the components. It uses forward slash, no, sorry, forward slash as an alternative. Let's say, for example, as Windows, the data may be stored in C, no, for backslash my documents backslash work, whereas in Linux it would be stored in forward slash home forward slash my document forward slash work, no. Partition, of course, another features, partition, directories, and drives. No? Linux does not use drive letters to organize the drive as Windows does. In Linux, we cannot tell whether we are addressing a partition, a network device, or an ordinary directory in a drive. Of course, another feature is the case sensitivity, no? So, in Linux, a file may have the extension .txt, but it is not necessarily necessary that a file should have a file extension. While working with shell, no, it creates some problems for the beginner. So, differentiate between files and directories. No, if we use the graphical file manager, it symbolizes the files and folders. Another feature, of course, of Linux is the hidden files. No? Linux distinguishes between standard files and hidden files. So mostly the configuration files are hidden in the Linux OS. Usually, we don't need to access or read the hidden files, no? Because the hidden files is in Linux are represented by a dot, no? Yung dot period before the file name. No? So to access the files, we need to change the view, no, in the file manager, or need to use a specific command in the shell. So when we install the Linux operating system, Linux offers many file systems such as the ext, ext2, 3, 4, JFS, RazorFS, XFS, BTRFS, and swap, no? So yun yung ginagamit ni Linux, no? Actually, the file system ext stands for extended file system, no, ext. It was primarily developed for Minix OS. So the ext file system is an old version and it is no longer used due to some limitations. So ext1 is the first Linux file system that allows managing 2 terabytes, no, of data. ext3 is developed through ext2. It is an upgraded version of ext2 and contains backward compatibility. The major drawback actually of ext3 is that it does not support servers because this file does not support file recovery in this snapshot. The ext4 file system is the faster file system among all the ext file system. It is very compatible option for the SSD o yung solid state drive disk and it is the default file system in Linux distribution. The GFS file system, GFS stands for what? GFS file system. Please encode in our chat box. GFS stands for Journal File System, and it is privileged by IBM for EIX Unix. No, it is the alternative to the ext file system. It can also be used to in place of ext4, where stability is needed with few resources. It is a handy file system when CPU power is limited. Another is Razer FS file system. No, Razer FS is an alternative to the ext3 naman file system. It has improved performance and advanced features. No, in the earlier time, the Razer FS was used as the default file system in SUSE Linux. No, but later it has changed some policies. So SUSE returned to ext3. The file system dynamically support the file extension, but it has some drawbacks in performance. XFS file system was considered an high speed, no, as high speed GFS, which is developed for parallel input-output processing. Actually, NASA is still using this file system with its high storage server, yung 300 plus terabyte server. We have also BTRFS file system. No, BTRFS stands for the B3 file system. It is used for fault tolerance, prepared system, PAN administration, extensive storage configuration, and more. It is not a good suite for the production system. And the last, of course, is the swap file system. No? The swap file system is used for memory paging in Linux operating system during the system hibernation. So a system that never goes in the hibernate state and required to have swap space equal to its RAM. Okay, so now we may proceed to, this is a week 3 segment 4, and we're going to wrap up our discussion of partitions and file systems. So to the extent that we're covering them on this high level. So when we left off in our previous video, no, we had shown that we can mount the file system what we created on our partition and then create files there, no. So perhaps now would be a good time to look a bit more closely into what types of files, and then the Unix file system support and how they behave before we then consider what partitions and file system are typically mounted, no. Okay, so Unix file system support and how they will behave before we then consider at what partition and file system are typically mounted on the system we considered in our discussions. So Unix file system is a logical method of organizing and storing large amount of information in a way that make it easy to manage. So a file is a smallest unit in which the information is stored. No, Unix file system has several important features. All data in Unix is organized into files. No, all files are organized into directories. No, and these directories are organized into a tree-like structure called the file system. Okay. So, but prior to that, I'll just want to play a video earlier, no, about this one. No, I think we're done on this one. No. Okay. Okay. So sorry. Now, files in Unix system are organized into multi-level hierarchy structure known as directory tree. No, at very top of the file system is a directory called root. No, which is represented by a forward slash. No, all other files are descendant of root. No, and we have of course the forward slash. No, bin, boot, dev, h, home, lib, meta, and so on and so forth. Actually, so the ordinary file is the file on the system that contains data, text, or program instruction. It used to store your information such as some text. You have written or an image you have drawn. This is the type of file that you usually work with. Always located within / under a directory file. No? Do not contain other files. In long format output of ls-l, no? This type of file is specified by the double quotation, actually the symbol, no? And the directories, of course, no? Directories stored both special and ordinary files. Now, for users familiar with Windows or Mac OS, Unix directories are equivalent to folders. So a directory file contains an entry for every file and subdirectory that it houses. No, if you have 10 files in a directory, there will be 10 entries in the directory. And each entry has two components. Number one, the file name, and number two, a unique identification number of the file or directory, or called the inode number. No. Another is the special files. No, used actually to represent a real physical device such as printer, tape drive, or a terminal used for input-output operations. No? Device or special files are used for device, no, on Unix and Linux system. They appear in a file system just like an ordinary file or a directory. In Unix system, there are two flavors of special files for each device. No, character special files and block special files. Actually, no. So the Unix file system has a disk, can be divided into logical partition, as I mentioned earlier, as described the MBR. A logical partition has a disk label describing the geometry of the disk and the file system partition. So, of course, a disk can be a file partition is a collection of cylinder group on which you can create a new file system. So, of course, we have also, before I forgot, we have a socket, no? A Unix socket, no, is a special file which allows for advanced inter-process communication. So a Unix socket is used in a client-server application framework in the sense it is a stream of data very similar to network system. No, but all of the transactions are local at the file system. So we have, as what we have here, no, we have the hard disk, no, file system, cylinder group. Each cylinder group contains a list of inodes as well as the actual directory and data blocks. So, of course, the data is here, no? The inode data, the file metadata, the data block references, and file data blocks, no? So, we have also symbolic link, no? Symbolic link is used for referencing some other file of the file system. So, symbolic link is also known as soft link. It contains a text form and the path of to the file it references. So, to an end user, symbolic link will appears to have its own name, but when you try reading or writing data to this file, it will instead reference these operations to the file it points. So, if we delete the soft link itself, the data file would still be there. No, if we delete the source file of the move it to the different action, symbolic file will not function properly, of course, no, and so on. So the Unix file system divided into cylinder groups. The file system metadata replicate in software blocks in each cylinder group. The file system block size and be different from its physical block size. Inode separate from data blocks. Inode density is fixed at file system creation time, and various options allowing tuning of file system to accommodate anticipated use. So this will be the references. I just want to play a video demonstrations on the Unix file system.
Hello, and welcome back to CS615 System Administration. This is week 3, segment 3. And after, in our last video, we explored what it means to be a file system, we'll now take a look at a slightly more sophisticated implementation, the Standard Unix File System, or UFS. The Unix file system is the historical file system implemented in version 7 of Unix, and subsequently superseded by the Berkeley Fast File System, also known as the BSD Fast File System, or FFS. Now, of course, there are many more types of file systems, and the implementations vary significantly between traditional file systems, journaling file systems, and things like ZFS, as we've already hinted at. However, the fundamental concepts remain the same. and so it's useful for us to consider how the Unix file system is structured. Now, recall from our last video that in our file system we quickly identified the need to allocate a storage unit for the data we wish to store, and that we then, equally as quickly, realized that we want to be able to associate metadata with a file, but that in doing so it would be useful to separate the metadata from the file data and storing it on different areas of the disk. We then constructed a crude file system format to accommodate this model, but of course a real file system will look somewhat different. So let's take a look. As we recall from our earlier video, a physical or virtual disk can be divided into logical partitions that may be described in, for example, the master boot record. Such a logical partition may be further divided into file system partitions. On BSD-derived systems, these partitions are described using a so-called disk label, which we've also seen before. The OS-specific partitions on which we may then decide to create a file system are comprised of cylinder groups, a concept that is applied even if the hardware backing the storage device were, say, an SSD, and thus really doesn't have any physical cylinders. Either way, we can now visualize our physical disk as looking like this. Now, since each partition comprises these cylinder groups, we have a need to describe them in a file system-specific manner, and to store some meta information about the file system itself. This data is stored in the so-called superblock, which we generally find near the beginning of the partition. If the partition is a boot partition, such as our primary OS partition, then it may also contain boot blocks at the beginning of the disk as well. Now, each cylinder group itself contains the actual data blocks, the parts where we store the actual bytes that make up our files, as well as a list of inodes and blocks set aside for the metadata associated with the inodes, the inode blocks. Since the entire structure of the file system is written in the superblock, it would be pretty disastrous if you lost this one block, so the file system replicates the superblock in cylinder groups, thereby allowing recovery of the file system from a corrupted superblock. Finally, the actual data that we discuss when we talk about files and directories are stored in different groups of data blocks, the inode data blocks and the file data blocks. Here we see how the metadata about a file, all the information that we came up with in the last video, is stored separately from the actual bytes of the files. As you can tell, we continue to strictly follow the evergreen mantra of CS, where one layer of abstraction reveals further layers as we dive deeper. But at least we end up with a reasonably easy to understand diagram such as this one. Now let's see if we can map our understanding from this diagram back to what we actually observe on the disk. Here we have our usual NetBSD instance with our extra volume attached. To inspect the properties for a file system, we can use the dumpfs utility, so let's take a look at the manual page. This tool allows us to see details about the superblock, cylinder group, and the inodes, for example. So let's give it a try. Look at that, no superblock. No surprise, we haven't created a file system on this disk yet. No file system, no superblock, no meta information about the file system, makes sense. So let's start by creating a disk label. We accept the default of just using a single partition spanning the entire disk here, since this is our second disk and doesn't require a boot block or a swap or anything. Okay, so dumpfs still doesn't know anything about this disk. So let's create a file system on it already. For that, we use the newfs tool. The newfs tool is used to create a new file system, and as you can tell, there are several useful options. For example, we can specify a file system block size. That is the smallest storage unit of our files. Note that this is a file system specific property. The storage device itself will, as we discussed in the previous video, have its own physical block size, commonly 512 bytes. Another option we can specify here is the total number of inodes to create, as well as several others. Okay, so let's create a file system on our disk. Here we go. We created a file system with the default 16K block size across 6 cylinder groups with 21,504 inodes each, and a superblock stored at these locations across the partition. Now that we have a file system, we can mount it and create our files on it. cat1, cat2, and snowcats. So now let's look at dumpfs again. With the file system created, we now get a lot of information displayed here, including about the cylinder groups. The dumpfs utility can also show us information about the inodes in use. Here we see the information for the files we currently have on disk, including their permissions, file size, their creation time and ownership, etc. We can compare with the output from ls and observe the timestamp via date. Inode number 2, by the way, isn't missing. It's the inode of the root directory on this disk. There it is, with size, owner, and group as displayed in the dumpfs output. If we run dumpfs with a v flag as well, then we also get information about all the inodes, including those that are not yet used. That is, we can see that our file system has indeed allocated a fixed size of inodes at file system creation time, and thus we are limiting how many files we can store on this disk the second we create the file system. In this case, that's 21,503 inodes per cylinder group, meaning we're maxing this disk out at just about 1.3 million files. Okay, time for another break. Let's summarize. We've seen that our file system divides the disk into cylinder groups. The information about the file system in cylinder groups is then stored in a superblock, which, to avoid it being a single point of failure, is replicated into the different cylinder groups, thereby allowing recovery and reconstruction of the file system even if one of the cylinder groups is corrupted from the alternate superblock. We also saw that our file system has the concept of a block size, the basic optimal I/O unit that the file system will fetch or write data in, and may be different from the physical block size of the disk. Next, and in alignment with what we had come up with ourselves in our last video, we want to separate where we write actual file data from where we write the metadata. This allows for more efficient storage and less wasted space, but also increases I/O efficiency, since often we don't really need to access the actual data of a file. Think about how when you run ls-l, you are retrieving and displaying all the metadata associated with a file, but not the contents. By separating the inode blocks from the data blocks, we can rapidly fetch all the metadata without having to seek to the data blocks back and forth. Talking about inodes, we observed that the total number of inodes, that is, the total number of files the file system can hold, is fixed at file system creation time. And that, together with the file system block size, are just two of the various things we can tune at file system creation time to accommodate the anticipated use of the disk. That is, If we know that this disk we're putting in place is intended to be used to store primarily a relative small number of really large files, then you might choose a different inode density and block size than if you wanted to store huge numbers of tiny files. In the first case, you'd use a larger block size to improve I.O. and select a smaller number of inodes and fragments. In the latter, a smaller block size and larger number of inodes. The FS manual page in section 5 has a lot more details here, and it'd be a good exercise for you to try to create file systems using different parameters and see if you can exercise and observe performance differences based on the different use cases. Alright, so with all this information and the exercises you've seen, we now have a pretty good understanding of the basics of the Unix file system. And although other types of file systems utilize different techniques to manage the storage space, a lot of what we discussed here remains directly applicable. So with that, we can finally move on to briefly summarizing the different file types we're dealing with, as well as some of their attributes, as well as talking about where we mount our file systems and what conventions exist for our file system hierarchy. Until next time, thanks for watching.
Okay, so this will be the discussion of the week 3, segment 3, of course. And after the video, we explored what it means to be the file system, and we'll know the slightly more sophisticated implementation, the standard Unix file system or UFX, and the Unix file system is the historical file system implemented in version 7 of Unix and subsequently superseded by the Berkeley Fast File System, also known as the BSD Fast File System or FFS. Now, there are many more types of file system as what we discussed, and the implementation varies significantly between traditional file system, journaling file system, and things like ZFS, as we've already hinted at. However, the fundamental concept remain the same, and so it's useful for us to consider how the Unix file system is structured. Okay, so this time we're going to discuss, of course, the week 3, segment 4. So again, as what we discussed in Unix and operating system inspired by it, the file system is considered a central component of the operating system. It was also one of the first part of the system to be designed and implemented, of course, in the first experimental version of the Unix. So let's have a look. Here's an MTN directory containing, as usual, the two entries that and that. References the current and parent directory respectively. We create a regular file which is then shows as such by leaving the first character of the first permission string as dash. And to do that, we use the ln command actually there. Now, these two files are indistinguishable other than by name. We have here the SSH pre-BSD, and by using -a, you name -a, we could be able to display, of course, this one. Then afterwards, we will be able, of course, to use the command exit at the same time. Then we could able to see the deb /xbd0a and xbd3a and xbd4a. So the file system hierarchy, the all partitions with the exemption of the root or back / partition can be mounted anywhere in the file system hierarchy. Now, many pseudo file system can be mounted to present system information or properties as if via file input output. So as what we have here, we have the / here being others whom and USR or user. The name, of course, like let's say Alice, Bob, then this will be the data in the public HTML, and so on. So this will be a layout of file system. So an outline of the file system hierarchy. So we have naming is very important because the Unix system relies on file name convention for much of its power as a system. So the following file system layout describe generally where things are and what they are with references to other main page for more detailed documentation. Not all files will be in every system. So the backslash, the root directory, the copyright, no, and the user file. No, when it comes to copyright, notice most often put on CD-ROM distributions. No, and this will be an example of exercises actually, and this exercises also continues up to the limitation of the file system. But I'll just want to play a video presentation. No? This will be the link, no, of the discussions of files. Okay. So if you have some questions, additional input, do not hesitate to post your question in our chat box for us to address as early as possible. Okay.
Hello, and welcome back to CS615 System Administration. This is week 3, segment 4, and we're going to wrap up our discussion of partitions and files.
Actually, I forgot, this is also a demonstration, of course, on how we'll be able to apply this one. Okay, it covered the week 3 and segment 4 discussion.
File systems, to the extent that we're covering them on this high level. When we left off in our previous video, we had shown that we can mount the file system we created on a partition and then create files there. So perhaps now would be a good time to look a bit more closely into what types of files the Unix file system supports and how they behave before we then consider and what partitions and file systems are typically mounted on the systems we consider in this class. Here, let's have a look. Here is an empty directory containing, as usual, the two entries dot and dot dot, referencing the current and parent directory respectively. We create a regular file, which ls then shows as such by leaving the first character of the permission string as a dash. Next, we create a directory, which ls then identified by a link D. Each of these is now an entry in our current directory. As we mentioned before, each file is referenced by an inode, which contains all the metadata associated with it, the permissions, ownership, timestamps, etc. And it is the file name existing in this directory here that creates the reference to the inode. And while we generally do not call them that, every single file name to inode mapping is called a hard link. But we can have multiple names for the same file. So if a file already exists, we can link another directory entry to it. To do that, we use the ln command. There. Now these two files are indistinguishable other than by name. More accurately, they are not two files, but they are two names for one and the same file. We can verify this by looking at the inode number of the files, which ls shows us by passing the -i flag. As we see here, our directory has one inode number, and the two regular files share the same inode. That is, as far as the system is concerned, they are the same file, and ls also tells us over here that there are two names for this file. This number here is the link count, the number of names that exist for this file in the file system. But there's also another type of link, a so-called symbolic link, which is created when using the s flag to ln. The difference here is now that we can see that the symbolic link is indeed a separate file. It has its own inode number, and the file type is shown as L. A symbolic link, then, is a special type of file that simply says, hey, don't look at me, look at that guy, for any operation. The ls command also shows us the target of the symbolic link in the output. So when we read the file, what we get back is the contents of the file it points to. Okay, so we've seen files of type directory, regular file, which is really only a different way of saying hard link, and symbolic links. But there are other types of files. One of them is a FIFO. A FIFO is effectively the manifestation of the concept of a pipe in the file system, and behaves just like one too. Anything written to the FIFO can be read from it in that order. ls, therefore, uses the p character to indicate a FIFO, also known as a named pipe. The behavior of a FIFO can be a bit surprising on first use, but to illustrate, let's start a process that reads from the FIFO in the background. We can then cat the symlink, which redirects to the regular file, into the FIFO, at which time the backgrounded cat process reads the data and prints it to standard out. When we hit return again, the shell tells us that the backgrounded process has completed. We also know that apparently not all messages generated by the shell correctly support UTF-8 characters, but it also serves as a good reminder that while file names can contain characters other than just ASCII, as we are showing here, that may not always be a good idea. Anyway, let's take a look at what other file types we can find. Let's create a few hard links to existing path names in the current directory. And then we ask the file command to report on all of them. There we go. Now we see a FIFO, a character special device, such as a TTY for example, a block special device, such as a hard drive, a directory, regular files containing UTF-8 Unicode, a symbolic link, and a socket, an inter-process communications rendezvous point in the file system that provides access to the sockets API for communications between processes on the same host. Here, ls-li shows us more information, where again the first letter of the permission string gives us the type of file. So those are the different types of files you will likely encounter in a normal Unix system. There are a few other types of files, but some of them are implementation specific to the operating system in question. Either way, let's now take a look at what file systems we find mounted by default on the different Unix versions we consider. First, FreeBSD. Here we see that the root file system is mounted from def gpt rootfs, suggesting the use of a GUID partition table. The mount command shows what file systems are currently mounted, and doesn't differ from the output of df in this case. Okay, so far so good, simple enough. Now let's look at OmniOS. We've done this before, but just to recap, when we run mount, we see a rather different view, with several other things showing up as being mounted. That is, we have our root file system, which we know to be on a ZFS pool, as well as several special purpose pseudo file system. Let's look at the Mount tab manual page. This is one of those weird things where we project information from the running system into the file system, making it appear as a regular file. So, looking at etc mount tab, we find no surprises. The same file systems mounted as shown before. How does the OS know which things to mount? Let's look at the VFS tab manual page. Now this is an actual file, a configuration file describing the defaults for mounting file systems at boot time. Let's take a look at that file. There. This describes which things to mount, as well as what type of pseudo file system to use for the given special mount point. Alright, now let's compare to Linux, and Fedora Linux in particular. Again, df gives us some information here, showing the use of some special file systems like tempfs as well as the disk-backed root file system. Now, if we run mount, then, whoa, that's a lot of things showing up there that we didn't see when we ran df. Look at all that. Fedora nowadays uses systemd to bootstrap and manage the running system, so we get a whole bunch of extra weirdnesses stashed in here. We see tempfs, defs, control groups, etc., etc., all with the respective mount flags shown here on the right. Let's see what man fstep says on this system. The etc fstep file contains information about which file systems can be mounted. When we look at the file, we note that it contains only a single entry for the root file system of type ext4 and mapped to the device with a given UUID. That is quite different from what we've seen currently being mounted, so where is that information tracked? etc mtep points to proc self mounts, using the procfs pseudo file system to reflect information about the running system into the file system hierarchy, as we mentioned before. Proc self mounts looks like so. Note that it looks like a regular file, but is of 0 byte size. Yet when we cat it, it shows us all the things just like the mount command did. So again, we notice a discrepancy between what file systems are available when running, for example, df to report on free space, and what other pseudo file systems are active. For many of the pseudo file systems, it simply doesn't make much sense to report file usage, since by definition they only abstract system properties into the file API. Now all this is a bit strange. We've talked at length about disks and partitions, but most of the things we've seen here are not really file systems, nor are they backed by disks. This is to illustrate how the file system API and concepts have been so successful that we've increasingly used it for other purposes. Secondly, it's worth noting that the default layout of the AWS instances we spin up do not necessarily represent those of actual production systems serving specific purposes. So let's instead show a different example. What you see here is the df output on the server on which the course website is hosted. This is a NetBSD virtual private server, but as you can tell, here we have a more normal layout. We have a root disk that provides the operating system and is, no surprise, mounted under /. But we also have additional disks for different purposes. We see one disk dedicated to the home directories of all the users on the system, and another disk mounted for miscellaneous data files. The OS also has a PTYFS, a kernelfs, and a tempfs mount, but nothing quite as crazy as the Fedora systemd instance. Okay, so let's visualize how we mount our disks. Even though nowadays we frequently have one monolithic partition containing absolutely everything, we still may see different disks mounted in different places. And this is really the only stipulation we have in mounting partitions. A partition can be mounted anywhere, with the exception of the root partition, which must be mounted under /. Now, way back in the olden days, when disk space was still expensive and sparse, it was rather common to have one disk that contained the bare minimum files needed to boot the system, and that partition would be the root partition, while another disk might contain all the additional files that would show up under user, for example, and end user's private files living on yet another partition. This, by the way, is one of the reasons for why we have a /user directory instead of just providing all files under /. We'll see in a second that there's actually some logic to this. Now, as we also just saw, there are other things we can mount, but those pseudo file systems don't get represented here in the graphic, since we want to draw a distinction between what data lives where. And for that, we probably also want to think about some sort of standardization across different operating systems and consider where we want to install software, a topic we'll go into much more detail in the next week's videos. And what do we do when we want to look up some information, such about which files go where, or what the file system hierarchy should look like? Nope, we don't type which files go where into Google and then follow the first Stack Overflow link to some random person opining that the kernel should go under /all my kernels. Instead, we pull up the manual page. Man here, provided by the OS, provides a description of the file system hierarchy. It notes, for example, that under bin we keep the utilities used in both single and multi-user environments. The system configuration files go under etc. It tells us where users' data goes, where libraries go, and notes that we don't want to rely on user being available, since it might reside on a separate disk not yet available at boot time. It tells us about the location for system utilities, thereby answering the question as to why we have both a bin and an sbin. Describes the user hierarchy itself, which somewhat mirrors the root hierarchy. And it tells us where various other files go, such as log files and PID files. So you see, all this has some logic and reason behind it, and having this hierarchy defined and then adhered to by software providers and system administrators makes it easier for you to both use as well as maintain the system. By careful separation of these files, you can use different partitions with different mount flags and security settings, for example, or you may be better able to budget your disk space, or avoid runaway processes eating the up disk space or inodes on one partition from interfering with operations of the system as a whole. Okay, this brings us to the end of our discussion of file systems and mount points. Here are a few things for you to think about and to experiment with. Take a look at the different mounted file systems in the different operating systems, as we've shown in this video. Make sure you understand the differences and identify what each is used for. Also take a look at the mount options, that is, the way in which the file system is mounted. Many file systems allow for different behavior based on the mount flags. You may, for example, be able to mount the disk read-only, or with certain properties enabled or disabled to boost performance. Make sure you understand what all the different flags mean and why they might be employed. We also saw that sometimes there's a discrepancy between what etcf step says should be mounted and what is mounted. Try to explain under what circumstances such discrepancies arise and whether or not that's a problem. Next, think a bit about the file system. Remember at the beginning of this topic we ran some experiments trying to fill up disk space and using up inodes? Rerun those exercises and see if things make more sense now, if you've gained a better understanding. Then think about specific limitations in the file system. For example, how large can a single file be? What limits its size? We saw that we can use, for example, UTF-8 characters in the file names. What other characters can you use? What characters can't you use in a file name? Why not? How long can a file name be? Try it out. Create a file name with 100, 200, or 2000 characters. What, if anything, is the limit? If there is a limit, why is that? Now take that thinking beyond the file name. If each component in the path name is a file name separated by a slash, and if there's a limit on the file name length, what's the limit on the path name? If a file name is nothing but a hard link, and if you can have multiple hard links for the same file, can you have 100, 2000? What, if any, is the limit? And finally, try to create a hard link across disks or mount points. You should find that fails. But why is that? If you are able to answer all these questions, then you'll be in good shape and think you'll have gained a better understanding of the topics we've covered so far. But we're not quite done yet with file system hierarchies, I'm afraid. As we've seen when looking at the Here manual page, there's a reason for why we put things into one place or another. But just how do the files get there? Well, we'll cover that directly and indirectly by way of software installation concepts in the coming videos.
Okay, so thank you very much for attending our class. So I hope that you will be able to learn our lesson number 2 no, or module 2. So next week, no, because this coming Thursday will be your next this coming Wednesday may be your activity. So next week we're going to discuss the software installation and multi-user basics. So stay safe everyone and God bless.